Ready? Yeah. All right, I think we will go ahead and get started. And look, the door closed magically.
Hey.
I was just going to holler at someone over there to close it, but it took care of it. All right, everyone hear me okay? What? All right. Who said that? All right, welcome. I'm Paul Lefebvre, and I have with me
Travis Hill.
whose mic's much louder.
Oh, wow, I am.
Booming Travis Hill. Luckily, or maybe not so luckily, he isn't talking quite so much right now. So save your ears. So we're going to be talking about LLVM, leveraging LLVM, a compiler overview. So before I jump right into some of the LLVM stuff, I thought I would hit what is a compiler. And the very simple statement converts source code to an executable app. I got a picture of my compiler book from when I was in school, 150 years ago. I keep it on my bookshelf behind me, in awe of it, mostly. That's called the Dragon Book. If you're totally, like insomnia is hit and you haven't slept in days, pick that bad boy up. It is dense. In the case of Xojo, we're generating native machine code, of course. And I was going to talk about that because Xojo's had a few compilers over the years. And I thought I'd just give you a little bit of background as to what they did and what they were. So the very first compiler, which I affectionately named the Generation 1 compiler, was the one in the first version of Xojo. And that was in use from 1998 to about 2004 or so. And that compiler built 32-bit x86 apps for Windows and PowerPC apps for Mac. I just said that. The Generation 2 compiler kicked on about 2004 or so. I'm thinking with Real Basic 5-ish is about when that compiler started showing up. And that one generated 32-bit apps as well for x86 and PowerPC, and it could generate Mac, Windows, and Linux. And now we are in the land of the Generation 3 compiler, which has been in place in the system since 2014 at various stages. And that compiler uses the LLVM project, and it builds 64-bit x86 projects. It builds 32-bit and 64-bit ARM code. And lots of platforms it can hit: Mac, Windows, Linux, iOS, Raspberry Pi, and I heard a rumor, Android. So what is LLVM? That's a bunch of letters. What does that actually mean? Well, I don't actually know that it means anything, but it is a library and tools for building compilers. Do you know that it actually stands for anything, Travis?
Oh, yeah, it's low-level virtual
Oh,
machine.
yeah, that's right. I don't think they go with that anymore, though. That probably was its
Yeah, it's
initial
probably.
thing. Yeah. So there you go. That's a low-level virtual machine is probably what it stood for. So you can check it out in all its glory at its website. And this compiler has widespread industry backing. It's used by companies besides Xojo, a few we may have heard of. We got small companies like Apple and IBM and Intel are using this compiler. It is very widely adopted. It's also used in production compilers. I should say the tool set's widely adopted, and it's used by production compilers for a variety of things. Clang, that's the C compiler. Languages such as D and Rust and OpenCL, Swift, of course, and Xojo are all using this. There's probably many, many more. This is just a great tool set. And it targets most modern architectures, which is, in the case of Xojo, we, at this point, are really wanting to hit x86, 64, and ARM, because that's what we want to target. But actually, LLVM targets all kinds of other processors, embedded stuff and other things. So why are we using LLVM for Xojo? The first two compilers, they were just built by Xojo. So why are we using LLVM now? Well, it's so we can respond to changing technology. In 2014, we had ARM for iOS, and that switched over to be 64-bit only in 2017. And then in 2015, we were able to add 64-bit for x86, and then 32-bit ARM Linux for Raspberry Pi. And because LLVM's already building that stuff, we can just do the additional hookups to Xojo and add that capability. And as Travis and everyone else likes to say, it's just a flip of a switch. See, it's easy. It couldn't possibly be easier. No, obviously there's still work involved, but there's a lot, as you're going to see later, that goes into a compiler, and it's good to get some of that stuff off your plate. So if we're not having to build a lot of that stuff, it's less code that we have to maintain and write, and that always results in fewer bugs if you're not writing code. What is the quote that everyone likes to say? The only code that doesn't have bugs is the code you did not write. So. And this future-proofs us. You've all heard rumors. Apple's like, oh my God, at WWDC they're going to announce that all Macs are now running ARM. That's definite. That rumor's solid. That is a solid rumor. So, in the past...
Wait, what?
You heard it here. Get it out on Twitter. And... But in the past, there was always a bit of trepidation. What is Apple going to do now? And then, that it could impact us greatly and freak us out. But now, we know that if they do something like that at some point, we're going to have the facilities in place to be able to deal with that. And the latest release of Xojo, 2018 R1, is actually using LLVM 6, which was released in March of this year. So we've got a very current version of LLVM in place, and we're really happy about that. And speaking of the compiler that's in the current version of Xojo, I want to talk about some of the recent compiler changes that have been put in place. And we now have 64-bit debugging on all platforms, Windows being the new one that was just added. And that required LLVM 6, which is kind of a reason why we had to jump up to that. And one of the reasons why Windows was the last debugging version to add. We also fixed some issues with currency types in the latest compiler. Not in this release, but I think that was in 2017 R3. iOS builds are now 64-bit only. Maybe you didn't even notice or care, but in the past they used to be technically universal binaries, which had both the 32-bit and the 64-bit code in them. But Apple is, got the sign 64-bit or bust, and they're starting to jettison 32-bit stuff, and they no longer need it for iOS as of iOS 11. And of course, I mentioned we upgraded to LLVM 6. A few other things of note, rather technical thing, but the structure alignment, when you're creating structures to interface with OS calls, you can put in a value of 0 to indicate that the compiler will do something called a natural alignment. And I think Travis might be able to answer any questions on that. I know how to write the words that are in this paragraph. But that's a particular way to make sure that your OS calls stay lined up, I guess.
Yeah, that's a pretty accurate way to
Okay,
put it.
Great. Gold star for me. Integer. Wanted to point out a few things to keep in mind when you're dealing with the integer data type. In 32-bit apps, if you use the integer data type, you're actually going to be getting essentially an int 32. So a 32-bit integer. That means it has a maximum size of whatever that happens to be. But it does have a lower limit that you can reach. In 64-bit apps, an integer is going to give you an int 64, which has a super high upper limit that you're not likely to reach. But you have to keep that in mind when, if you have 32-bit apps that you're now switching over to build as 64-bit, the size of your integer has changed. And that, for most of your code, is totally irrelevant and is not going to affect anything. But if you do have declares and things like that, you do need to look them up to see if the actual OS call expects a 32-bit or 64-bit integer, or one that's very specific, and you have to declare it. Yes, Chuck?
What does this mean for Booleans? How are they stored?
What does it mean for Booleans? How are they stored? Well, Booleans are not integers.
There's no Boolean primitive in the CPU, right?
There's no Boolean primitive in the CPU.
Yes, the way we internally work with Booleans has not changed and isn't relevant between 32 or 64-bit.
Yeah, I don't know specifically of the Boolean implementation, but yeah, as Travis said, that's not a change between platforms. This is not a change, but it's more of just something you want to be aware of if you're using variants in your apps. There is a type integer property on a variant that gives you the value of the variant in integer form. But unlike the integer data type, type integer is always int 32. It is never int 64, even on a 64-bit system. So if you want to get the 64-bit value out of a variant, you need to specifically call the, I guess it's type int 64, and use that instead. And you'll probably have to use, you know, the compiler directives to have your code appropriately set up. And we also added a special compiler warning to help people out with declares. And this is primarily if you happen to put a declare in global code so that it tries to run it on a platform where it makes no sense, it's going to tell you, you know, hey, dummy, you're on a Mac, not Windows, or vice versa, whatever. So you can see here it's telling you that, you know, user32 is a library on Windows in this case, not on Mac, as opposed to just, you know, giving you a very generic error or crashing out if it attempts to call something in the OS. All right, so that was a bit of background on LLVM. And just to give you an idea of how that's used in Xojo. Now I want to go through how a compiler at a super high level kind of operates and functions through a very tiny bit of code so you can see what's going on here. So our compiler consists of two main parts. You've got the front end and you've got the back end. Now in the case of Xojo, the LLVM part we're using is the back end part because that's the part that's going to be generating the source code. But there's a lot of work that happens before generating the executable code. But there's a lot of work that has to happen before the executable code gets generated. And in this case, there are lots of components. You have your lexer, you have your parser, you have your semantic analyzer, you have your, what the heck does IR stand for again?
Intermediate representation.
Intermediate representation, right. And then once that is generated, it gets fed off to an optimizer, and then eventually an actual executable code generator. And that is done repeatedly throughout your project whenever you hit the run or the build button. And once you have all your source code generated, you got your executable code bits. At the very end, you have a little tool called the linker that takes all these various components, puts them all together, packages them up into a runtime executable format expected by the operating system so you can actually run your app. So what is a lexer? Well, this processes your source code. It turns it into a stream of tokens, essentially, you know, taking that, you know, stuff out and lining it up so that the next steps in the system will have parts that are easier to understand. So we're going to take a look at this very simple line of code. And it's just a simple mathematical function. And it's just a variable being assigned some calculation. So the lecture is going to go through and identify the components of this. So we start with, we have here something was identified called sum. This is tagged as an identifier. Its value is sum, that's its name, and its position in the source code is also noted. And as you see, we go through here, each of the components are identified. So now we have a token that is used for equals or assigns, and its position is noted. We have a value that is identified as a double, and its value is noted as 314, and its position. Another operator is found and tagged, and another, this case an integer, is found in the list, the multiply operator, and then the last integer. So this is all put together and kind of separated out so that the parser now gets that information. So each step of these compiler things is attempting to take the source code that you wrote and simplify it down so it can get to a point where you end up with something you can run. So this now turns those tokens that were generated by the lexer into a fun concept called abstract syntax trees. And again, that's light reading in that book I showed you earlier. So here we have each of the tokens that were identified. And the first one was the identifier, and that is a variable. And the next thing was an operator, the equals or assigns operator. So you can see we're starting to build a tree here. So the assignment is pointing to the variable. And now the next thing we found here is, okay, we got a double. That had a specific value. I believe that was 314. Yep. And you can see that here is now part of the tree. So this tree is telling us that the assignment points to both a variable and a double literal. Now we have the plus operator. Well, where does that belong with? That actually is part of the assignment, and based on order of operations, ends up in this position in the tree. And then the rest of the values start to get added in the same pattern until you end up with your full tree for that simple assignment. So you have your assignment happening at the top. On the left-hand side is just the variable, and on the right-hand side is the calculation itself following standard order of operations. So now we reach the next part of the compiler, the Semantic Analyzer, which is going to validate that the code makes sense, that you didn't write gibberish. None of us ever write code that doesn't compile, right? The code's perfect every time. So this part of the compiler we could all just check off and not need to run, but you know, that's maybe not true. So here, this part of the compiler is adding in some stuff behind the scenes to make sure that everything looks good. In the case of Xojo, those values are being cast to the appropriate types so that the actual math, I guess, is going to work in this case. And so the tree is modified a little bit, made sure that everything looks good. In this case, we didn't have a syntax error or anything like that, so the Semantic Analyzer is pretty happy about that. Excuse me. Now it's time to take a look at the intermediate representation, so the IR generation. So we have here our syntax tree. And we need to go through it. So you can see it follows the tree. And it looks like that's going down the side there. That's probably depth first, I think that sort of lookup is. So we've got our first value. And you can see the code here. That's not real easy to read, is it? That is IR, the IR that LLVM used. And it's its own little language. So that first line is saying multiply two 32-bit integers together. And then I forget what the other is. Something to floating point, I think that.
Yeah.
But as you can see, very, very cryptic code here is what you're getting. Floating point add for the value, and then floating point something.
Signed integer.
Signed integer, yes. You know, that's good old one-letter acronym going right there to remember those commands. Luckily, no one has to code in IR. That is all machine-generated stuff. And then lastly, that is actually stored in the variable. So the result of all that calculation that got put in the temporary variable at the end is stored. So all your Xojo code eventually gets generated into this IR. And then now we've reached the end of the front end. The end of the front end. Don't get that image in your head. But we're at the end of that part of the compiler. So the front end has done its work. So now we're reaching the back end of the compiler, and this is where LLVM starts to come into play. And this takes the intermediate representation, and it is emitting the executable code. So we're getting closer to having an actual app, but we're not there yet. So as I mentioned before when I went through the compiler generations, the 32-bit backend, the 32-bit compiler, is something that was developed in-house by Xojo. And it is very fast to generate code, very fast, but it does no optimizations whatsoever. It just spits out that code as quickly as it can for you. What we're going to be talking about is 64-bit and ARM, which are using LLVM. Now, the big thing that LLVM is giving us is an optimizer, totally unavailable before. And I put here in quotes, this is improving the intermediate representation. That's its goal in life, to make things better. And what it attempts to do is transform the code in some way to make it perform better. Now, from what I understand, there's no real solid math behind a lot of this optimization stuff. A lot of it is stuff that people have figured out. A lot of it is heuristics. But the goal is to have code that runs equivalently to how it originally ran, but is more efficient. So here's an example of an optimization called loop unrolling. So it repeats the contents of the loop rather than doing the branching. So instead of your code chugging along and then having to call a branch and then sending it back up, that, depending on what you're doing, could be very expensive for the CPU to be doing. So you can unroll your loop. And then when you unroll the loop, you might have additional optimizations that can be done. So here we have a very simple loop. Doesn't do too much. And you can see how it's structured here. So the value is increased, it goes back up, and once it's over, it jumps out of the loop. Well, it turns out that you can start to realize that, well, I don't really need all those steps. Oh, I'm sorry, I missed one thing. Xojo incorporates into the all of its loops, you may recall, these yield statements that you don't specifically have to add. This allows Xojo's cooperative threading model to work. So that gets inserted into the loop by the various processes. And you can turn that stuff off by disabling the background tasks. So, boom, they're gone. And then the end result is you just have a single call that was able to do the beep thing, and the loop was eliminated. The other type of optimization that can be done is dead code elimination. So this is code that you've written that's in your project, but actually is never used. And because you have no code path that gets to it. So this is a process where your app is put together as a graph, another fun topic that's in that book there. And you start at the beginning, and you just kind of iterate through the code, note all the code paths, connect everything up, and when you have everything connected, you're like, oh, I had one there that wasn't connected to anything. Well, that one can be lit on fire, and it's not needed. You cannot possibly cause a problem because that code was never called. You can also do dead code elimination at link time, and this is a bit more high level. It operates at the function level, so it just determines if you have high-level code that you aren't running. But the important thing to remember is that if you reference a class at all, it's going to bring in all its methods. Doing that also brings in all its superclasses. And that also brings in anything that is referenced on any of that stuff, so properties, parameters, return types, that sort of thing. I think I saw this on the forum yesterday or today. Someone was asking a question about constants and if it was expensive to have a constant defined in your code, if that sort of thing ended up getting reassigned each time the code was run. And constant folding is where, no, that isn't. Any expressions that are constants are just evaluated immediately so that they don't have to be evaluated again. In this case, this is just some simple math, not an actual constant declaration, but you can see here that 1 plus 2 is obviously 3, and the compiler can figure that out and use that in its place every time, so there's no math operation that's happening in your code. And this is actually required for some of the syntax things so that declarations like this actually work like you expect. So what are some of the optimization choices? Well, I want to just point out that with LLVM, and if you're building a 64-bit app for Xojo or ARM, you can go to the shared build setting, which is right there, and there's a setting called optimization level. And there are a few options. Can you guess what its default value is? It's default. Now remember, this does not work with 32-bit. So if you're building something 32-bit, changing this has no effect whatsoever. Obviously, we go with the default one because that is the one that has the fastest compiles. And there are two other options. You can go with moderate, which improves math performance, but the compile time does slow down a little bit. And then you can go with aggressive. And who doesn't want to have aggressive code? I mean, we all do. And this is going to provide the best math performance, but compile times can slow down a lot, a little bit. It's going to be slower no matter what. And the important thing to note on these optimizations is at this point, they're going to work primarily with, extensive math code that you have, math manipulation, operations, that sort of thing, because, framework code's already pre-optimized. It's not going to pick up any additional optimization from this. Oh, sorry, Chuck, I didn't see.
Okay. So I think you answered my question, but so in a typical web app, there's no point to do aggressive optimization because you're swamped by the TCP stuff.
Right, so the question is, in a typical web app, does it make any sense to use aggressive optimization? I don't think it really is going to make much sense for a typical web app.
No, the general answer is no.
Yeah.
And what I tell most people about picking optimization is you don't need aggressive unless you already know you need it. So.
Right, that's it. It's like the introspection feature. When you don't need to know what it is until you know you need it. So what are some Xojo features that affect its ability, or LLVM's ability to optimize your code? Well, first of all, it's built-in exception handling because exceptions can be raised at any point in your code, and that causes obvious branch jumps when an exception is raised. So that can impact how the optimizer is able to handle things. The way that Xojo does its object destruction can also affect how LLVM is able to optimize things. Speaking of introspection, in order to introspect your code, you need to have extra stuff in your project. It's built in there, essentially. So that means that some things that maybe could be stripped out won't get stripped out so that they can be introspected at runtime. And of course, the thread yielding that is kind of inserted for you behind the scenes affects looping and other things, and that can affect LLVM's ability to optimize. And not to mention, as you kind of see here, basically it's all the safety features that are in Xojo that allow you to write code more easily without crashing your system. So the nil object checking, the stack overflow checking, the bounds checking, all that stuff has extra things in there that the optimizer has to either work around, deal with, or maybe ignore in the interest of safety.
And most of those things at the bottom have pragmas that you can turn off if you happen to know you don't need them, but you need to focus on speed.
Right, and you don't want to ever be in the habit of just saying, oh, I'm always going to add this to the top of all my methods because speed wins. That's a little dangerous. And then, of course, you have plugins in Xojo, which can affect optimization because those are just linked in a big chunk. They're pre-built, essentially, so they're not compiled at all. So now we get to the code generation part, and this is what emits the machine code. So if you take a look way back when to our original code we had, which was just a simple calculation, the constant folding optimization is going to result in that simple math being calculated out to a value of 11. And not a coincidence that comes down to just one line of source code, which is good. But not source code, but machine code. I guess machine code is somewhat source code. And technically, I don't think this is machine code. This would be assembly, yeah. I guess. But you can't really show machine code. It would just be some bits, and that's hard to understand. So that's what the ARM instruction looks like. And you can see the 64-bit version looks different. And the x86 versions look like that. So different code is obviously generated for each platform, but you get to not worry about that through the joys of LLVM. Now you're just about at the end. Your app has been, quote, compiled. You get a bunch of components that are all down to machine code that by themselves individually don't do anything. They're kind of useless because you got to link all that stuff together to make an actual app. So I wanted to point out the formats that Xojo uses, or that Xojo's linkers use to generate your apps. So on Linux, we're generating ELF app formats. So that's the executable and linker format. That's pretty common. I believe that's also what we're using on Android.
Yeah.
Yep. And for Apple's products, we're using macOS and iOS. We're using the Mako app format, which that is an old format. That goes back to the next days, right?
It's been around for a while.
Yeah. But that's the standard format for Apple stuff. And then on Windows, it's the PE format for portable executable. And all that is done using the LLD linker. And that is a platform-independent linker. It's part of the LLVM project. I guess a sub-project would be the way to say that. Yeah, and it's even got a subdomain, so you can see it there. So what's happening with the compiler beyond this? Well, we got a few things that have been talked about. I keep hearing people talk about Android, so I put on the slide. But apparently we're working on Android, and the compiler obviously needs to know about that. It was news to me. Right? What can I say?
It would be better if you were working on actual Androids.
Actual Androids would probably be helpful, although sometimes they rise up and kill you. Yeah. That's always a downside. Enabling LLVM incremental compilation. Most of you have seen LLVM compiler is slower than the older 32-bit compiler. We want to get that speed up a bit so that it is faster and more fun for you to just stick with 64-bit when you're working, because 32-bit is withering on the vine on many platforms. Travis talked about position-independent executables that are needed for Android, and that work to add it for Android is going to be available for all the other platforms that are able to make use of it, so that is going to be pretty helpful. That's a big security thing. And then we're going to continue to evaluate LLVM upgrades as the LLVM project itself adds features and enhancements to see what's appropriate for Xojo and what we can add that will make Xojo better. And that is my screaming fast compiler overview talk. And now Travis and I are going to attempt to answer any questions you have as best we can. All right, we'll go around. Start with you.
So is that part of that LLVM incremental compiler work? Is that going to eventually get us back some of the build times we lost? Because right now, whenever I build a large project, I get this assembling code. 2 minutes later, the project's built. It used to be the second time you would build it, as long as you didn't touch any of those things, you got it back in 30 seconds.
Right.
So are we ever going to get that?
So the question is that incremental compiler going to help with these build times that are long and consistent? They never improve as you're doing subsequent runs.
And the code hasn't changed.
The compiler just throws everything out.
Right.
Yeah, that's exactly what that line item was talking about. We haven't brought over incremental compilation yet, but we know you want it because we know we really want it. We work in a huge project. Oh yeah, we're 64-bit all the way now, so we really, really want that.
Yeah, that will be nice.
Is that a priority? Or?
That's important.
It's at least important. Fred, you had a question.
What are some of the benefits of LLVM 6 moving there other than Windows? And with your work for Android, will the other frameworks benefit from that other than what you pointed out?
So the first part of that question was, yeah, I am.
Okay.
The first part of the question is about LLVM in version 6, and what does that give us? Well, internally, it gave us a few convenience methods that we could use. LLD, the linker, was updated so we can control it a bit more, give it a bit more hints about what we want included and what we don't. As far as Xojo code generation itself, it hasn't changed that much, which is also why we skipped from 4 to 6, because we evaluate every version. If it doesn't help Xojo, there's not much point in spending cycles on it. But I would say the major impact for end users has been Windows 64-bit debugging availability. And then your next question was?
Android work and it benefiting the other frameworks.
Oh yeah, I think at the compiler layer, it's certainly the work on Android. How does that benefit the others? Well, the position-independent code is a big benefit, and that's probably the largest one. Some of the work we're doing to bridge between virtual and native code doesn't really apply to the other platforms, but is quite useful for Android specifically.
Jim?
If I recall correctly, years ago we were told that this transition to LLVM would help with debugging, and that we could have more debugging features like conditional breakpoints and things like that. Is that still true, and is that coming down the road? Anything in that area?
Well, okay, the question was, does LLVM enable debugging improvements like conditional breakpoints or a bunch, various debugging things? The answer to that is a little complex, but LLVM does provide more hinting by default that we can utilize for some of those debugger improvements. It doesn't give them to us for free. If it did, they would already be there. But some of those, I would say, we're evaluating now, but they haven't shown through the product quite yet.
All right, Gerard in the back.
Maybe a future hypothetical. There's talk about Apple moving to ARM chips for Windows. Do you think that would be something you guys would think would be a pretty good transition to use at the time, or easy in your experience? If it happens?
So the question is, with this rumor about Macs utilizing ARM CPUs instead of Intel CPUs, is that fairly easy for Xojo to manage? And while I hate the word easy when I think about all of these tasks to do, we are well prepared for that. We can build those frameworks and the compilation on ARM if that were to occur. So I think we're in a pretty good place for that particular eventuality.
Yes, Ken.
Maybe this is something I can imagine. Obviously, on one platform, on one host platform, you can build for all of the targets. So if you're on a Mac building a Mac desktop and building for both Windows, 64-bit, and Mac OS, everything is great. I found that if you do the same on Windows, but you also cross-platform build on the Windows platform as a host for Mac OS, what the packaging of the executable Mac package is all of a sudden a visible folder system. Maybe I just imagined it, because if you move that back to a Mac, I didn't try it, but I wonder if that would work. If that's a function of LLVM.
Let's see if we can repeat that question, Ken. So the question is, if you're building on Windows for other platforms, is the built app packaged properly enough to get it to the other platforms? And my understanding is when you do that on Windows, you get I think a tar file.
Yeah, for a 32-bit Mac app, it should work, and it should be an archive that just moves right over, and just don't extract it until you move it over to the Mac, and then it should work just fine.
What about the 64-bit?
The follow-up question was, what about building a 64-bit Mac app from Windows? Well, that is an interesting conundrum, because we're actually waiting on the linker. If you remember, we're waiting on LLVM to enable Windows 64-bit debugging. Well, LLD is not a mature Mach-O linker yet, and we need it to be in order to build these and link a Mach-O executable on Windows and Linux for Mac. And they are working on that as we speak, and we will be very happy to plug that in when it's available.
As for 32-bit, I've done it because I developed for Windows primarily, and it did make that RAR file, tar file.
Right.
And I'm like, what do I do with this? So I just took it over to the Mac, and the Mac just knew what to do with it, and it installed it and said that. So.
All right, great. Yep, Youssef.
So, I think a while back you said that the LLVM not supporting the Raspberry Pi Zero processor was a reason to compile for that. Has anything changed in that in LLVM 6?
So the question is LLVM support for the smaller Raspberry Pis, like the Zero. Is there any support for that?
The answer is no, it hasn't changed anything, because the problem actually isn't the LLVM compiler. It is our framework requires ARM v7 or higher. And the likelihood of us going back to enable older ARM architectures on the framework, I don't think there's enough bang for our buck there.
So we were hoping a new 0 comes out that's a little beefier.
So no 6502 support either?
So the question is, when will we add Commodore 64 or Apple to 6502 support? Yeah, that'll come soon, I'm sure. GUIs might be a problem. Any other questions? Oh, we got one here from Steve.
Truthfully, it may not be an LLVM. It has to do with following external libraries and ways to support that.
That's not a question.
I'll take it offline.
All right, Steve's question is being taken offline as he ponders it. Tom in the back, did you have a question way back there? Yell it out.
So on a Mac, when you're making debug builds, and watching the activity monitor, and actually going into the process, you see what's the inconsistencies and so on, advantage of multiple processes. Is there any scope for multiple processes being leveraged in that point? At the moment, it seems like most of the build process only uses one core.
Okay, so the question was, you can see if you watch your activity monitor, you can see at some point all of your cores being utilized, but not through the entire compilation process. And the question is, well, are we going to do more to do more multi-core? And the answer is yes, we do intend to. The first thing that we're doing right now is what was mentioned, which is incremental compilation. That will help regardless of whether it's single or multi-core. But after that is when we're evaluating more of the build process using more cores.
Justin.
On Linux, are there plans to make a single bundled application versus just creating a binary with the icons and a separate PDB folder?
So the question was, is there any chance on Linux for it to be a single executable rather than separate files with the icons and other libraries, et cetera? And I'm not aware of any plans, but that's more at the framework layer. So you and I should go talk to William about that.
I asked William about that yesterday on Windows, and he said no.
Oh, well, the follow-up was I asked about Windows, he said no. And the answer absolutely on Windows is no. Microsoft does not recommend it, does not support it, and will not support us if we try and jam all that into one executable. So we cannot do that on Windows. Linux is a slightly different thing, so we can talk about that later.
All right, thanks everyone.